In section 2 of the circle unit, we're going to talk more about some other interesting properties of circles and chords and tangent lines in those circles. So the first thing we're going to talk about is inscribed angles. And an inscribed angle is an angle inside the circle. The interesting point for this one is the vertex is on the circle. Okay, so B as the vertex has to be on. And we're going to see that this angle cuts this arc out. And when we talked about central angles in the last section, the central angle and its arc were equal. In this case, we have a different relationship, which should feel pretty good in your heart. If I'm going to move this vertex, obviously it's not going to be equal. And what's going to happen is that the arc is going to be 2 times the angle, or the angle is half the arc. So we have this relationship of doubling or halving, whether you're going in or out. So if we look at a couple of examples, it's kind of that angle chase idea that you have to work your way through. I would never worry about finding it in this order. So let's just start here. This angle X is going to cut out this arc right here. When I go back in, it gets smaller. That means X is 50. When I look at finding Y, that cuts out this arc. When I go out, I double to 68. Now, to find Z, I have to do a little more detective work. If you remember, all the way around is 360. So really, in this case, to find that missing arc here, let's call it W, so that I can then go back in and find the angle, I have to take 360 minus 62 minus 100 minus 68 minus 76, and when I do that, I get that the arc is 54. And then when I go in for the angle, I'm going to cut that in half, and so Z is going to end up being 27. So it's just a little bit of patience and a little bit of angle chasing. Now this one, there's 2 different ways to think about finding X. The first way is if I look at this side and I go in, that's going to get cut in half. And so if we call this Y, angle Y is 127, and then Y and X are a linear pair, so 180 minus 127 gives me that 53-degree angle. Or if I wanted to do it a different way, I could look at the arc here is 254, so that means 360 minus 254, this is 106. Cut that in half, and I end up with 53. So again, it isn't a right way or a wrong way, it's how you see these different layered concepts coming together, which is what makes geometry so much fun. Perpendicular bisector theorem. Now, we've had the perpendicular bisector theorem before, and it most often was associated with that triangle picture that looked like this. And then we knew that these guide wires were equal. We knew the angles got bisected, and we had all of those 4 properties. If we look at it in terms of a circle, this also makes sense. These equal parts by the perpendicular bisector theorem from Unit 2 are actually the radius, and so of course they're equal. And we know that here's our perpendicular, it's going to bisect this chord. It is not going to bisect this radius. So that is a key piece to keep in mind. OC is not bisected, and that's going to make for some interesting problems, but this is still a radius of OC. So let's look at some applications or some problems. The other cool part, before I move on, is that the arc also gets bisected. So arc BC is equal to arc CA. And that's going to be a useful property also. So if we look at an example, given the circle Q, W to X is 10. So right now we know that X to R is 10. Arc WPR, now yes, that's a minor arc and we're using all three, but we're doing it for clarity. So if the whole arc is 150, we know it gets bisected, so we know this is a 75 and a 75. We want to find a bunch of different things. So what all do we know right now? We know that our radii, we know that our chord gets bisected, we know our arcs, and we can start working through some things. So WP we already have marked, that's 75. WR is the entire chord, 10 plus 10, so that is 20. Now, with one more piece of information, that QX is 5, what is QP? Well, QP is a radius, and so one thing you're always going to want to consider doing in these perpendicular bisector pictures is drawing in the radius, because when you do that, you make a right triangle. And so for clarity, if we pull that right triangle out, Q, X, P, here's the right angle, I was given this as 5, I was given this in 10, then it becomes a really straightforward Pythagorean theorem problem. And so remember, you can always draw that radius in to complete that triangle. And when we work that out, we end up with C being the square root of 125, or approximately 11.2. Another useful theorem about circles is the perpendicular tangent theorem. So if a line is tangent to a circle, and tangent to a circle means it touches in just one spot, then it's perpendicular to the radius. And you can always count on that. So if you know the line is tangent, you get the perpendicular radius. If you know you have a radius and it touches the tangent line, you know it's perpendicular, because this is an if and only if. So we know it works both ways. Another super useful theorem that we have is the congruent tangents theorem. If it says if two segments are drawn from the same exterior point, like C out here, and are tangent to the same line, they go back and touch at one spot, A and B, then those segments are congruent. And that might seem kind of strange until you look at what actually happens in here. If I complete the drawing, those two, these are radii, so I know that they are equal. And if I draw in that diagonal, I have a kite. And with the right angles and the diagonal, I have HL, and by CPCTC, those outside chord segments, or secant segments, are equal. So just kind of a quick overview proof of it, but it should feel pretty good that it makes sense that if I have this outside point, that the segments touching it back to the same circle at right angles is going to be equal. Plus, it makes a kite. So why don't you go ahead and jump over to the second video for the last few examples.